how data transforms from segments to packets to frames to bits as it moves down the stack. We start with the upper layers in data. This is the raw message that's formatted for software before delivery instructions even exist. This is the actual payload, like the text of an email, a file you want to download, or a video stream, sitting at the application layer waiting to be sent. Then we have segments, which is in the transport layer. Data is broken down and wrapped in a header containing port numbers. If the data is too large to send at once, this layer chops it into smaller, manageable pieces so it can travel smoothly across the network. This step ensures the correct application receives the data and helps sequence pieces. This source and destination port numbers tell the receiving computer exactly which app, like a specific web browser tab or an email client, needs to open the data, while sequence numbers help put the chopped up bits back together in the right order. Moving into packets, in the network/internet layers, the segments are wrapped into an IP header containing source and destination IP addresses. At this point, the data becomes a packet and gets the logical tracking information it needs to travel across entirely different networks. This acts like a shipping label so the router can guide data between networks. Just like a mail carrier looks at a zip code, a router will look at an IP header to figure out the best path to get the packet closer to the final destination. Then we look at frames in the data link layer. Packets are wrapped in a header with a MAC address and a tailer for error detection. This creates a frame which handles the physical hop-by-hop delivery rather than the long-distance journey. This ensures that the data safely reaches the exact hardware neighbor on the local network. It uses physical MAC addresses to move the data from your computer to your local router, and the trailer at the end acts as a security check to make sure the data didn't get corrupted during the handoff. Then we have bits in the physical layer. Frames are converted into a stream of ones and zeros. The digital frame can't travel through a cable as text or code, so it must be translated into pure binary data. They're transmitted as electrical pulses, light signals, or radio waves across the media. Depending on the connection, those ones and zeros travel as voltage changes on copper wire, flashes of light in a fiber optic cable, or wireless frequencies in the air. And then lastly, we have the decapsulation process. This is where the host reverses these steps, peels off the envelope until only raw data remains. When the data reaches its destination, the target computer strips away the frame header, the IP header, the transport header, and reads the instructions at each step until it delivers the clean, original message to the application. So moving on, we have the layer 4 transport. So we have the TCP transmission control protocol. This uses connection-oriented philosophy focused on absolute reliability. TCP treats every piece of data as critical, ensuring that nothing is lost, corrupted, or left behind during transmission. It establishes a formal three-way handshake before transmitting data. Before any real information is sent, the sender and receiver exchange controlled packets to synchronize their connection, making sure both sides are ready and capable of communicating. It numbers every segment for sequencing and requires acknowledgement for receipt. The sender tracks every single piece of data it sends out, and it waits for the receiver to send back a message saying it got it. If an acknowledgement does not come back, the TCP sends that piece again. It features error recovery and automated flow control during network congestion. If the network starts getting bogged down, TCP will automatically slow down its transmission rate to avoid crashing the connection, and it will reconstruct any data that gets corrupted. This is critical for web browsing, email, and file transfers. You need TCP for services like HTTPS, SMTP, or FTP, because if you lose even a few bytes of data when downloading a website or application, the entire file could be corrupted and useless. Then we move into UDP. This uses a connectionless philosophy focused on max speeds. UDP doesn't care about reliability or tracking. The only goal is to get the data out the door as fast as possible. This uses a fire and forget logic with zero handshakes or acknowledgements, checking to see if the receiver is ready, and the sender never asks for confirmation. It just sends the data and immediately moves on to the next packet. Okay, sorry about that. It pushes bits as fast as hardware allows without tracking order or delivery success. If packets arrive out of order, or if they don't arrive at all, UDP doesn't attempt to fix it. It leaves those issues up to the application if they matter at all. It features extremely low overhead with no retransmission delays because the header is extremely small and never pauses to resend missing data. It never creates the artificial delays or lag that you sometimes get with TCP. This is critical for live streaming, online gaming, and DNS requests. In a live video call like this or a multiplayer game, a dropped packet is old news instantly. You don't want the connection to freeze while trying to recover a frame for 2 seconds from 2 seconds ago. You just want the current frame right now. And then we have the technical trade-off of the two. TCP gives us guaranteed delivery, ordered sequencing, and slower transmission rates. The heavy checking, tracking, and constant back and forth communications means that you get perfect data at the cost of speed and bandwidth, while UDP gives us the best effort delivery, potentially jumbled sequencing, and faster transmission rates. You get an incredibly fast, lightweight stream of data, but you have to accept the risk that some pieces might get lost along the way. You choose TCP when data integrity must be perfect, and UDP when it must arrive right now. It's a direct trade-off between accuracy and speed, which is exactly why the internet relies heavily on both protocols to function. Moving on to layer 3, this is the network and internet, where logical addressing and how the IP protocol handles the routing packets between networks. For logical addressing, the IP addresses are logical and change based on your location rather than being permanent. Unlike a physical MAC address that's burned into your network card at the factory, an IP address is assigned by the network you're currently connected to. This means that your IP address changes when you move from your home Wi-Fi to a coffee shop. The network ID represents the neighborhood, while the host ID represents the specific house. This division allows routers to effectively move data. They don't need to know where your exact computer is right away. They just need to find the correct overall network first, just like mail delivery looks at the city and street before the house number. The subnet mask acts as the map that defines where the network portion ends and the host portion begins. This tells the device exactly how many bits of the IP address belong to the network identity and how many are left over to identify unique devices on the local network. Then we move into the routing process. The IP is connectionless and best effort, focusing entirely on finding the next physical hop. It doesn't set up a connection beforehand or verify if the destination's online. The only job is to look at a packet, pass it along to the next closest router in the chain. Computers route traffic destined for external networks directly to a default gateway. When your device realizes a destination IP is not on the local network, it doesn't try to map out the whole internet path itself. It simply hands the packet off to your local router, which serves as the exit door to the outside world. Routers check internal routing tables to match destination IPs with the best exit ports. Every time a router receives a packet, it scans its memory for the most specific match to that destination address, determining which cable or interface it needs to shoot the data out of the router. Strip the old layer 2 frame, read the layer 3 packet, and wrap it in a new local frame. As data travels across the internet, the outer link envelope is constantly discarded and rebuilt because the Wi-Fi frame can't travel over fiber optic internet back fiber optic internet backbone connection. The router opens the frame, checks the IP inside, and rewires the frame for the next leg of the trip. And then the packet lifecycle controls. Time to live counters drop by counters drop by 1 at every router hop to destroy looping packets. If a packet gets stuck in a routing loop due to a misconfigured network, it'll bounce around forever and crash the hardware. The TTL field acts as a self-destruct timer, dropping by 1 at each router until it hits 0 and gets deleted. IP serves as the core delivery envelope for both IPv4 and v6 structures. Whether you're using the traditional 32-bit IPv4 addresses or the massive 128-bit IPv6 addresses, this layer acts as the standardized packaging that allows different generations of systems to communicate. ICMP transmits critical error status updates and handles diagnostic utilities like ping. IP itself can report errors, so it relies on ICMP to send messages back to the source if a network is unreachable or a packet dies, which is exactly how tools like ping and traceroute check network health. And then we have ARP. This resolves logical layer 3 IP addresses into physical layer 2 MAC addresses. Before a packet can actually walk across a local network cable, your computer has to find out which physical hardware chip owns that target IP, and ARP acts as the lookup directly to bridge that gap. Layer 2 data link, physical addressing MAC in the role of Ethernet in hop-to-hop delivery. For physical addressing, the MAC address is burned into the network interface card like we talked about earlier and stays with the hardware forever. Unlike a temporary IP address, this is a 48-bit physical identifier unique to the specific piece of hardware, meaning it acts like a digital fingerprint for the device. This acts like a structural identifier that only carries significance on the immediate local link. The internet at large doesn't know or care what your MAC address is. It only is used by the devices that are plugged into the exact same local switch or connected to the same wireless access point. Routers use local hardware addresses to target specific machines on their connected branches. When a router needs to hand a packet to a computer directly connected to it, it uses a MAC address to find the exact network card of that machine. The role of the Ethernet serves as the dominant standard formatting data into local network frames. Ethernet defines the exact rules for how bits are packets, how networks detect collisions, and how hardware talks over physical cables or local connections. It wraps the layer 3 packet inside a frame header containing the source and destination MAC addresses. Before the data hits the wire, Ethernet slaps this header onto the front, ensuring the local network switches know exactly which physical port needs to receive the data next. It appends the frame check sequence trailer for mathematical error detection. This trailer sits at the very end of the frame and contains a value calculated from a math formula run over the entire package before it was sent. Receiving devices calculate the trailer data and instantly drop corrupted frames. When the next device receives the frame, it runs the same math. If its answer doesn't match the trailer, it means the data got corrupted in transit, so the hardware quietly deletes it without waiting for an explanation. Does someone have a question? I'm sorry. Okay. I thought I saw the hand raised thing. Okay. So now we are on. Okay, great. Sorry about that. Okay. So we move on now to hot-to-hot delivery mechanics. The IP addresses remain completely unchanged as a packet travels across the network. The source and destination IP addresses stay exactly the same from the moment the packet leaves your computer until it hits the final server across the world. MAC addresses are completely stripped and replaced at every single router hop. Because MAC addresses only work as local lanes, every router along the path needs to every router along the path peels off the old layer 2 frame, looks at the destination IP, and wraps the packet in a brand new frame with a new MAC address for the next leg of the journey. Laptops address original frames to the local default gateway hardware. When you send a packet to a website, your laptop doesn't put the website's MAC address in the frame header. It puts the MAC address of your local router because that is the immediate next hop. Routers rewrite the frame with their own exit port as the source and the next router as the destination. As the packet hops across the network, the frame is constantly rewritten, changing the hardware addresses to match the specific two devices currently talking over that local cable. And then we have local switch operation. Switches operate at layer 2 by managing internal MAC address tables. A switch listens to the traffic moving through it and builds a map, learning exactly which physical MAC address is plugged into which physical port on the back of the device. Traffic is directed solely to that specific port, matching the destination hardware address instead of broadcasting to everyone. Unlike old network hubs that blasted data out of every single port, a smart switch reads the incoming frame header and forwards the data only to the specific wire where the destination machine is waiting. Now we go on to the application layers. For the unified approach, the TCP/IP application layer handles all operations before data reaches the transport layer. Rather than passing data through 3 separate phases on its way down, a program prepares its messages entirely within its own environment before sending it directly to layer 4. Software developers build session and presentation features directly into the app logic. This means that the code you write to run a web app or an email client takes care of the user's sessions and data formats internally, rather than relying on the operating system's network stack to handle it. Moving on to how the missing OSI layers are absorbed. Layer 7 application functionality provides the visible software interface and core protocols like HTTP and IMAP. This is the part of the software you actually interact with, where protocols define how your browser requests a web page or how your email client pulls the message from the server. Layer 6 presentation functionality is absorbed by apps handling their own encryption and data translation. Rather than a dedicated network layer managing file formats, the application itself compresses the images, reads the JSON files, and negotiates the TLS encryption. Did someone have a question? Layer 5 session functionality is replaced by the application level code using cookies to track user login states. The network connection does not keep track of who you are. Instead, web applications use session tokens and cookies inside the data payload to remember you're logged in when you click the link. The strategic benefits of the collab starts with the network infrastructure not needing to understand data formatting to successfully move packets. Routers and switches along the path don't care whether you're streaming a video, sending a text, or downloading an encrypted file. They only look at the transport and network headers to do their jobs. It reduces the protocol overhead and administrative red tape within the data headers. If we use the strict OSI model, every packet would need extra headers for the session and presentation layers, which would waste bandwidth and make processing slower. This grants developers freedom to define custom formats and session rules without waiting for new network standards. You don't have to update the world networking hardware just because you invented a new video file format or a faster way to authenticate users. You just update the application. And then we move into the operational role. This acts as a comprehensive service provider managing name lookups, IP assignments, and web requests. This layer is where critical utility protocols like DNS find IP addresses for domain names, and DHCP automatically assigns IP addresses to devices when they connect. It processes formatting and conversation management internally before handing raw data blocks down to layer 4. By the time the application layer finishes its work, the data is packaged into a clean, complete block of information, ready for the transport layer to split it into segments and start the delivery process. Moving on to real-world troubleshooting using the OSI layers as systematic bottoms-up approach for diagnosing network failures. The bottom-up strategy is a systematic engineering methodology that eliminates variables from the physical layer up. By starting at the very bottom, you prove that each foundation piece is working perfectly before you even bother checking the more complex software settings above it. This prevents wasting time on software configuration when a baseline connection component fails. There's no point in reinstalling a web browser or changing your DNS settings if the actual problem is just an Ethernet cable that got kicked out of the wall. We have layer 1 physical validation. This focuses on hardware verification, checking for active link lights, frayed cables, or disabled Wi-Fi toggles. You're looking at the actual physical world here, making sure copper, fiber, or radio waves are capable of moving data. Success means physical indicators are active and the hardware path is clear. Once you see the solid blink lights on both ends of the connection, you can officially check off layer 1 and move up the stack. On layer 2 data link validation, we verify if local hardware can successfully communicate with the immediate switch or router. Now that the wire works, you need to prove that your computer can format frames and talk to its closest neighbor. It checks for a valid MAC address, registration, and monitors logs for frame transmission errors. You're looking to see if the local switch recognizes your device and isn't dropping your traffic due to hardware mismatches or bad data frames. This utilizes the ARP-A command to confirm visibility of the local default gateway hardware ID. Running this command shows your local address resolution table and proves whether your computer has successfully discovered the physical MAC address of your local router. Layer 3 network validation. This confirms logical routing capability and verifies the system isn't stuck with an auto-configured AP/IPA address. You're checking to see if you have a real IP address from your network, or if your machine gives up and assigned itself a useless default address starting with 169.254. This utilizes ipconfig or ifconfig alongside an external ping 8.8.8.8 command. First, you run the configuration command to verify your IP and subnet mask are correct. And then you send a ping to a known public IP address like Google's public DNS. Success here means receiving active replies from an external IP address outside your local broadcast domain. If the ping responses come back, you just proved that your packets can successfully route out of the building and across the public internet. Then we move into layer 4 transport validation, where we validate if the remote server port is actively accepting connections or blocked by our firewall policy. Just because you can ping a server doesn't mean its specific application is running or available to you. This utilizes a targeted connection tool like Telnet or testnet connection on explicit application ports. You use these tools to test a specific doorway like trying to open a TCP connection on port 80 for web traffic or port 443 for secure traffic, confirming if the service is listening. And then we have layer 5 through layer 7 application validation. This isolates application defects once baseline connectivity, routing, and port access are confirmed operational. If you get this far, the network itself is totally fine, meaning the issue resides entirely within the software or data payload. It investigates DNS name resolution failures, expired security certificates, or invalid browser session cookies. This is where you figure out if the website name is misspelled, if the server's security certificate is broken, or if your stored credentials are causing a login loop. It utilizes diagnostic utilities like NS Lookup, browser developer panels, and localized application logs. You use NS Lookup to see if your DNS server can convert to the website name into an IP address. And if you open up your browser's developer tools to see the exact error codes the web application is throwing back at you. So then we move into the anatomy of a packet. So the header operates at layer 2 and layer 3 to provide routing and switching instructions. You can think of this as the mailing envelope that wraps around your data, containing all the administrative metadata needed to get the packet where it needs to go. Stores the source and destination physical MAC addresses for local switches. These addresses change at every single stop along the way, ensuring local hardware knows exactly which physical machine to pass the data onto next. It stores the source and destination logical IP addresses for internet routers. These addresses are permanent throughout the entire trip and serve as the ultimate starting point and final destination markers for the packet. Defines the protocol type to identify the traffic as TCP, UDP, or ICMP. This flag tells the receiving device exactly what kind of tracking rules are being used and how to handle the data once it arrives. It features a TTL value to prevent infinite data loops. This is a counter that kicks down 1 every time the packet passes through a router, automatically destroying the packet if it gets stuck traveling in circles. And then it utilizes a checksum string to verify the data wasn't corrupted during transit. The sender runs a quick math calculation on the header and writes the results here, allowing routers to run the same math and drop the packet if the numbers don't match. The payload operates at the upper layers and contains the actual data for the application. This is the interior content of the envelope, meaning it is the actual message or asset you're trying to move across the network. It holds the core content, such as web page pieces, email snippets, or video fragments. It's the raw cargo, like the actual text of your message or the piece of an image file that your browser is waiting to display. It's left completely unopened by local switches and routers during transits. Middle boxes and networking hardware only look at the header. They don't need to peer inside the payload to see what you're sending, which keeps the data moving efficiently and securely. And then it features a variable size that adjusts based on the maximum transmission unit limit, or MTU. The payload can grow or shrink depending on the network rules, capping out at a specific size so it doesn't overwhelm the network cables or hardware. And then we see how infrastructure uses the envelope. Switches inspect the outer layer 2 MAC addresses to forward it to the specific port. When a frame hits a local switch, the hardware looks at the destination MAC address and immediately shoots it to the exact wire leading to that device. Routers inspect the layer 3 destination IP to determine the next network path. When the packet exits your network, the router reads the target IP to figure out which backbone carrier or distant network needs to take the packet next. And then routers rewrite the layer 2 envelopes with the new MAC address at every single hop. The router strips off the old local hardware address, updates the source MAC address to its own, and sets the destination MAC address to the next router down the line. Then we move on to the three-way handshake. This happens, as we can assume, in 3 steps. Step 1 is the syn or synchronize. The client initiates the connection request to the server. This is the opening move where your computer reaches out to a remote server, like a web server, to announce that it wants to start a formal conversation. It generates a random initial sequence number to begin tracking data bytes. Rather than starting at 0, it picks a random number. We'll call it X, to act as a baseline for security and tracking so it can keep everything in the correct order later on. It flips the syn bit to 1 in the packet header envelope. This bit acts as a digital flag inside the TCP header, signaling to the server that this packet is explicitly a request to synchronize clocks and start a connection. This carries 0 application payload data at this stage. There's no website content or message data inside the packet. It's pure administrative request used solely to open up the communication channel. Then we have the syn act, synchronize, acknowledge. The server acknowledges the client's request and requests its own connection back. The server receives a request, agrees to talk, and says it wants to track data coming back the other way too. It flips both the syn and act bits to 1 in the header envelope. By raising both of these flags at the same time, the server tells the client that it approves the connection request and is simultaneously asking to sync its own data sequence. It sets up the acknowledge number to act equals X plus 1 to prove it received the client's packet. By taking the client's original sequence number and adding 1 to it, the server mathematically proves to the client that it successfully read the original message. This generates its own unique random initial sequence number. Just like the client did, the server picks its own separate random number. We'll call it Y to track the data in the data bytes and send it to it. Track the data bytes it will send from its side of the connection. And then step 3, the act, acknowledge. The client confirms the receipt of the server's response to complete the handshake. This is the final step where your computer tells the server that it got the approval and that both sides are officially on the same page. It flips the act bit to 1 and turns off the syn bit. The synchronization phase is finished, so the client lowers the syn flag and leaves only the acknowledgement flag active to confirm everything is set. It sets the acknowledgement number to act equals Y plus 1 to validate the server's sequence. The client adds 1 to the server's sequence number, proving that it successfully received the server's syn act packet. It advances its own sequence number to sequence equals X plus 1. The client moves its own computer forward to match the step the server is expecting, finalize the alignment between both devices. This opens the virtual pipeline so the payload data can move immediately. Now that the three-way handshake is complete, the reliable connection is established, and the client can immediately start sending actual application data like web requests or file uploads. Then we have sequencing and acknowledgement. Keeping track of data order, it assigns unique sequence numbers to every single byte of the payload data sent. Instead of numbering the packets themselves, TCP numbers the actual bytes of data rather than the packets, giving it an incredibly precise way to track exactly how much information has been sent. It uses the initial sequence number from the handshake as the starting baseline. Since that starting number is randomized for security, all of the following numbers build sequentially on top of that original value throughout the entire connection. It calculates the next sequence number by adding to the payload length to the current sequence number. If your current sequence number is 1000 and you send a packet containing 500 bytes of data, the next packet you send will start with a sequence number of 1500. It reassembles the packets that arrive out of order due to tracking different network paths. Packets can take an entirely different route across the internet, meaning the end of a file might show up before the middle, but TCP looks at the sequence numbers to put everything back into the perfect original order before handing it to the application. It drops the extra copies of data if network glitches cause duplicate transmissions. If a glitch causes a packet to get duplicated along the way, the receiver checks the sequence numbers, realizes it already has those exact bytes, and throws that extra copy away to avoid corruption. It keeps score through sending ACK numbers indicating the next byte the receiver expects to get. When the receiving device sends the acknowledgement, it doesn't just say it got the data. It explicitly tells the sender the exact byte number it wants to see next. It uses cumulative ACKs to confirm receipt of all bytes up to that specific port in one message. If a receiver sends back an ACK number of 3,000, that single message tells the server that every single byte from number 1 up to 2,999 arrived safely and perfectly. It refuses to advance the ACK number if a packet in the middle of the stream goes missing. If packets 1 and 3 arrive before but packet 2 is lost, the receiver will keep sending ACK messages asking for packet 2, completely halting the progress bar until that specific hole is filled. It saves out-of-order packets in a temporary buffer memory while waiting for the missing pieces. While the receiver is stuck waiting for that missing packet 2, it doesn't throw away packet 3. It holds on to packet 3 in the temporary storage so it can instantly stitch the whole thing together once packet 2 arrives. And it handles lost mail by launching a retransmission timeout clock the moment the packet is sent. Every time the sender releases a packet into the wild, it starts a countdown timer to manage how long it's willing to wait for a response. It fires a packet again if the timer expires before the ACK arrives from the receiver. If the clock hits 0 and the sender hasn't heard back, it assumes the packet was dropped by the router or lost in transit. So it automatically resends a fresh copy. This triggers an immediate resending if the sender receives 3 identical duplicate ACKs for a missing byte. If the sender sees the receiver asking for the exact same missing piece 3 times in a row, it knows the packets behind it are arriving, but the specific one is definitely gone. It bypasses the countdown timer entirely during a fast retransmit to keep data moving fast. Instead of sitting around waiting for retransmission clock to run all the way down, the 3 duplicate ACKs tell the sender to cut the line and resend the missing piece instantly, which prevents lag and keeps the stream flowing smoothly. We have flow control and windowing. The window size concept, this declares how many bytes of data a device can store in its receive buffer. This value acts as a buffer status report, letting the sender know exactly how much memory the receiver has left to hold data before its application processes. It uses a 16-bit field and TCP header to constantly update the sender on available space. Every time the receiver sends a packet back, even if it's just a basic acknowledgement, it includes its current window size so the sender can adjust its speed on the fly. It stops a fast sender from drowning a slow receiver or overloading a busy CPU. If a powerful server tries to blast data at a legacy device or a busy smartphone, the receiver can shrink its window size to force the server back off, preventing the receiver's memory from overflowing. This allows continuous data transmission without waiting for an ACK after every single packet. Rather than sending one packet and pausing to wait for a reply, the sender can continuously stream packets until it hits the total byte limit defined by the window size, making the connection much more efficient. For the sliding window mechanism, this dictates the maximum volume of unacknowledged data permitted on the wire at any one time. This mechanism sets a strict limit based on how far ahead the sender can get, ensuring it never has too many unconfirmed packets floating around in transit. This moves the transmission boundary forward at the moment a valid cumulative act arrives. The receiver confirms it got the older bytes. The window slides forward over to the next block of data, freeing up the sender to release new packets into the network. This locks the upper boundary in place if the receiver stops sending updates. If the acknowledgements dry up or stop arriving, the window cannot slide forward, which naturally chokes the traffic flow and prevents the sender from creating further network congestion. It tracks the bytes already sent and the act byte sent and act, bytes sent but unact, and bytes ready to send. The sliding window divides all your data into these distinct categories, acting as a dynamic visual timeline that tells the system exactly what's done, what's pending, and what can go next. And then we have dynamic window scaling and controls. This sends a window size of 0 when the receiver's buffer fills up completely. When a device gets bogged down and its memory is totally packed, it sends a 0 window announcement to pull the emergency brake on the connection. It forces the sender to halt all data flow instantly to avoid dropping packets. The moment the sender sees that 0 window flag, it completely stops transmitting new blocks because it knows that any extra packets sent would just get dropped by the overwhelmed receiver. This prompts the sender to dispatch tiny 1-byte window probes periodically to check if the space is cleared. Once halted, the sender doesn't just sit there forever. It occasionally sends single byte pokes to ask the receiver if its application has processed the backlog and reopened the buffer. This uses a window scale option during the handshake to expand the default 64 kilobyte limit up to 1 gigabyte. The standard 16-bit field only allows a maximum window size of 65,535 bytes, which is way too small for a modern high-speed internet connection. So this scaling multiplier expands that buffer space to handle massive modern data streams. This is where I start getting a little longer. I'm going to start just reading from here. So then we have the termination phase. We have the graceful exit, which is the 4-way handshake, or FIN. This is triggered when a program finishes sending data and flips the FIN flag to 1. Step 1, FIN. The closer sends FIN equals 1 packet and enters FIN wait 1 state. Step 2, ACK. Receiver sends ACK. The receiver sends the ACK entering closed wait while the closer drops the FIN wait 2. The receiver acknowledges that it got the request, but it keeps its own sending line open just in case it still has a few packets left to finish delivery. We have half-closed state. The closer can no longer send data, but still can receive data from the passive side. The connection is literally operating in one direction now, meaning your computer can listen to the last remaining pieces of data coming in, but can't upload anything else. Step 3 is FIN. Once finished sending the remaining data, the receiver transmits its own FIN packet. The receiver completes its final chores, shuts down its half of the connection, and sends its own finished flag out to the closer. Step 4, the closer sends the final ACK and enters a temporary time wait state. The closer confirms it received the receiver's finished packet, officially closing the loop on both sides. And the safety net is that it holds the connection open for 2 maximum segment lifetimes to ensure the final ACK arrives safely. If that final acknowledgement packet got lost in the network, the receiver would get stuck, so the closer waits around in silence for a short period of time to make sure it doesn't need to resend the confirmation. Then we have the panic button connection request, or reset. Sorry. This abruptly tears down a connection immediately without a polite multi-step handshake. This is the emergency eject button used when something goes completely wrong or there's no time or ability to have a structured conversation. This flips the rest bit or reset bit to 1 in the TCP header envelope and requires 0 acknowledgement back. There is no back and forth communication here. The sender blasts this packet out and considers the relationship over on the spot. The receiver doesn't reply with an X. It simply destroys the socket configuration instantly. The moment a machine gets a packet with the reset flag raised, it deletes the connection history from its memory and stops listening. It's fired by hosts when receiving unexpected packets for a port that's closed or non-existent. If a computer tries to connect to a web server on a port that isn't running a web service, the server sends back a reset pack and tells the client to stop bothering it. This is triggered by a computer that crashes, loses power, or suffers a sudden memory resource wipe. If a server suddenly reboots in the middle of a file download, it loses its connection logs. So when it comes back online and receives old packets, it uses the reset flag to clear the slate. It's injected by firewalls or intrusion prevention systems to kill unauthorized sessions. If a security appliance detects a cyber attack or a policy violation, it'll forge a reset pack and send it to both devices to forcibly kill the connection. Then we have FIN versus reset. FIN is triggered naturally by an application closing its communication stream. It's a normal software behavior that happens every time you close a web page or finish a clean file download. Reset is typically forced by the operating system kernel network stack due to errors. This represents an abnormal condition where the system has to intervene because the application layer can no longer manage the connection. FIN allows all remaining packets in transit to be delivered and read safely. This guarantees that whatever data is already traveling through the internet cables gets assembled and read before the lights turn off. And then reset dumps all unsent or unread data in the buffer into the trash immediately. This cuts the cord without warning, meaning that any packets sitting in line or halfway across the network are discarded and lost forever. So then MTU and fragmentation, the maximum transmission unit, or MTU, sets the maximum packet byte size allowed on a physical network interface. This defaults to 1500 bytes for standard Ethernet LAN, counts layer 3 IP header plus layer 4 data load payload toward total. Sorry, I've got my notes mixed up here. Counts both the layer 3 IP header and the layer 4 data payload toward the total byte limit. The entire layer 3 packet must fit inside this budget, meaning if your IP header takes up 20 bytes, you only have 1480 bytes left over for your actual data stream. This eliminates the need for network hardware to process infinitely long streams for continuous data. By capping the packet size, switches and routers can clear their memory buffers, ensuring that a single massive file download cannot hog the physical wire and freeze out other users. This enables jumbo frames up to 9,000 bytes and storage networks to significantly boost throughput. In specialized environments like data centers and network-attached storage setups, raising the MTU cuts down on header overhead and reduces processor strain, allowing for servers to move massive blocks of data much faster. For the IP fragmentation, this happens when a packet size exceeds an egress interface's MTU. It chops the original data section into smaller pieces to match the limit and copies the original baseline IP header onto every single new fragment. This flips more fragments to 1 on all pieces except the last one. Inserts byte offset values into headers so receivers know the piece order, and it postpones reconstruction until all fragments reach the destination host. The downside of this is that it taxes the main processor of the intermediate routers splitting data on the fly. It also drops the entire original packet if just one frame is lost or corrupted, and it exposes the networks to DOS attacks using overlapping offset values. The DF flag in PMTD modern fix. This flips the don't fragment bit to 1 on the IP header to forbid intermediate router splitting. And by setting this flag, the sender explicitly tells the routers along the path that is forbidden to chop the packet up. This forces the router to drop the packet and reply with an ICMP type 3 code 4 message. If it's too big, when a packet with don't fragment bit turned on hits a restrictive pipe, the router is forced to discard it, but it sends back an error message saying the destination is unreachable because the packet's too large. It uses these ICMP error messages to dynamically calculate the smallest MTU across the entire internet path. This process is called path MTU discovery, where the sender keeps throwing out packets and listening to the router feedback until it figures out the absolute narrowest bottleneck on the way to the destination. This shrinks the sender's packet size automatically to ensure zero fragmentation happens along the route. Once the sender knows the limit of the narrowest bottleneck, it adjusts the settings to stay safely under the threshold of the conversation, keeping the traffic efficient and preventing any fragmentation from occurring. Then time to live. The purpose of time to live, or TTL, is it sets a strict expiration limit on packet lifespan, 8-bit fields, and layer 3 IP header, the hop limit in IPv6. This kills packets caught in endless routing loops and saves bandwidth by stopping warp-in traffic. The countdown works by the operating system injecting the initial value like 64, 128, or 255. Every router will subtract 1 from the counter upon handling, and it functions as a physical hop counter, not a clock. The router drops packets instantly if it hits 0. The death notification ICMP time exceeded. The dropping router will alert the sender if the ICMP type 11 code 0 message hits. The router doesn't just quietly delete the packet. It takes a moment to write a note back to the source machine to explain what went wrong. It sends the router's IP and dead packets header back to the source and notifies the app that the destination couldn't be reached. TTL can be weaponized through trace route mechanics. It maps the network hops by using intentional packet death to discover the exact path to the server. Trace route completely flips the purpose of TTL on its head, turning a basic safety feature into an incredibly powerful diagnostic tool. This sends the first probe packet with a TTL of 1, forcing the first router to drop it and reveals its IP. Because the packet dies instantly at the very first hop, the closest router sends back an ICMP error, giving you the identity of your local default gateway. This increments sequentially to TTL2, TTL3, and so on, forcing each consecutive router down the line to reply. By gradually increasing this counter, you force every single router along the path to step forward and identify itself one by one. This identifies exactly where a path breaks down by pinpointing which hops stop returning ICMP errors. If your trace route gets all the way to hop 7 and then returns nothing but blank stares, you know exactly which router on the internet is dropping your traffic or suffering from a configuration failure. Stateful versus stateless flow. The differences between a single packet and a stream of session. For stateless flow, this is the isolated event. It evaluates each packet as an independent, isolated transaction. It keeps 0 records of previous packets or conversation histories. It looks strictly at static attributes like IPs and ports. It requires minimal CPU and RAM since it tracks nothing. It's used in standard IP routing, basic ACLs, and UDP. And it can't detect if inbound traffic is a real reply or spoofed. For stateful flow, this is an ongoing session. This monitors conversation life cycles and from handshake to termination. It maintains dynamic state table tracking sequence numbers and flags and treats individual packets as pieces of continuous stream. It verifies inbound packets are logical steps in established sessions and consumes memory to hold and update active session entries. This powers stateful inspection firewalls and NAT tracking tables. A real-world comparison, we can look at a stateless guard, which checks ID for every single entry, instantly forgetting cases. And a stateful guard checks an ID once, grants a wristband, and remembers the faces for free movement. Firewalls handle things differently. A stateless firewall requires separate, explicit manual rules for both outbound and inbound traffic, while a stateful filtering automatically allows inbound return traffic if the session table proves an internal device initiated the request. Then we looked at MAC addresses. A MAC address is a unique 48-bit binary number burned into network cards at the factory. It operates at level 2 and handles local network data delivery. This is shown as a 12 hexadecimal digit split by colons or hyphens. This is assigned through the OUI structure. OUI, the first 24 bits, identifies the specific hardware manufacturer, while NIC specific, which is the last 24 bits, acts as a unique factory serial number. And this guarantees no two network chips globally share an address. This doesn't change because it's physically etched into a read-only memory as a burned-in address. It can't be altered by standard software, operating system updates, or reboots, and it provides a permanent layer 2 anchor for reliable local switch mapping. The software exception for spoofing, operating systems can mask hardware IDs by sending a fake MAC. Modern devices do this to randomize MACs on a public Wi-Fi and stop tracking. And then we have the logical identity, which is the IP. And the purpose of this, the IP in global routing, is a structured hierarchical naming system for global routing. It's grouped into logical blocks instead of flat like MACs. Routers read network prefixes to find the next hop, and they stop transit routers from needing the exact physical locations. For public IP addresses, the scope is globally unique addresses. It's globally unique across the entire public internet. For routing, it's fully routable. No two online devices share one. For assignment, it's managed by registries and leased by ISPs. And for accessibility, it's reachable by any online device globally. Private IP addresses, RFC 1918. The scope is unique only within a specific local network. It's non-routable. Public routers drop these packets. It's handed out by local routers using DHCP and reused inside millions of networks without conflict. RFC 1918 address ranges. We have the 10.0.0.0/8, 16.7 million addresses. These are large enterprises or data centers. 172.16.0.0/12, it's 1 million addresses, which are medium businesses and campuses. And 192.168.0.0/16, there's 65,000 addresses, home routers, and small businesses. These connect through network address translation, or NAT. This acts as an intermediary boundary between private and public links. It swaps private source IPs with the router's single public IP. This tracks translations in a table to map traffic accurately and reverses the swap when the internet replies come back. application doorway or ports. Ports divide one IP. So we can look at one network interface running multiple apps at the same time. Software entry points are numbered 0 through 65,535 in layer 4 headers. Operating systems read destination numbers to route data to the right app. So we have several categories for port numbers. We have the well-known ports, which are 0 through 1023. These are reserved for core system and internet services, which need admin rights. We have the registered ports, 1024 through 49,151. These are used by specific vendor software, databases, or game servers. And then we have the dynamic or ephemeral ports, 49,152 through 65,535. These are temporary ports assigned to clients for return traffic. Some standard services in their assigned ports include HTTP on port 80, which handles the unencrypted website data transfers with TCP. We have HTTPS on port 443. This handles encrypted web requests through SSL and TLS on TCP. SSH on port 22 allows secure remote command line server management over TCP. SMTP, which is port 25, routes mail messages between distribution servers through TCP. And then DNS on port 53. This translates human-readable names into logical IP addresses, and this uses both UDP and TCP. Some real-world transaction examples. Tracks channels using socket IP address plus port number combination. Web request user connects to 203.0.113.50 on port 443, and the OS passes the data to a web server. The admin login, you connect to 203.0.113.50 on port 22. The OS routes traffic to an SSH daemon, and then both streams share the same wire and IP without getting mixed up. Layer 2 versus Layer 3 delivery. The split responsibility is hop by hop versus end-to-end. Layer 3, the IP, handles end-to-end delivery. Original IPs remain unchanged across the journey, while Layer 2 handles MAC, which moves data across the immediate local wire. These are stripped, like we talked about, and rewritten at every single hop. This moving across the local switch, Layer 2. This operates entirely at Layer 2 with no understanding of IP routing. It maps physical hardware ports to connected MAC addresses using MAC address tables. It inspects the incoming frame header to find the destination MAC address and forwards traffic directly out of the matching port while ignoring the internal IP data. Layer 3, moving across a router, takes over when the data must travel to a completely different network. This modifies the local Layer 2 hardware headers while keeping Layer 3 logical headers intact. Step 1 includes leaving the local host. The host realizes the target IP is external and targets the default gateway router. Source IP 192.168.1.10 is the local host, where the destination IP is 8.8.8.8, which is the remote server in Google's IP. The source MAC is the host ID going to the destination MAC, the router's local interface ID, and the local switch reads the destination MAC and delivers the frame to the router. Step 2, the router's decision. The router receives the frame, strips the Layer 2 header, and evaluates the Layer 3 IP header. It reads the destination IP to find the final target location. It consults its routing table to calculate the best next path to that network and identifies the next hop interface leading towards the upstream provider. And then step 3, rewriting the header. It overwrites the hardware addresses entirely before sending the packet out egress interface. So the source IP 192.168.1.10 stays the same, while the destination IP stays the same at 8.8.8.8. The source MAC changes to the router's outward-facing interface ID, while the destination MAC changes to the next upstream device's hardware ID. MAC header rewriting repeats every single router until it reaches the final destination. Well-known versus ephemeral ports. The split direction design. Every connection requires two ports, a listener, server, and a talker, the client. The server, well-known ports, are static and predictable so clients can find the service, while the client or ephemeral ports are temporary and random to receive replies without local conflicts. Well-known ports 0 through 1023 are the static targets. These act as publicized, designated phone numbers for specific services. The listener role is reserved for core infrastructure, and services waiting for inbound traffic. OS privileges require admin or root rights to bind any port under 1024. And for consistency, this provides consistency through worldwide uniform. Port 443 is almost always HTTPS. Ephemeral ports, the 49,152 through 65,535. These are short-lived throwaway ports allocated automatically by the client OS. Purpose here is to segregate returning data streams when a client opens multiple connections. The OS picks a random unused number from the dynamic range for outbound traffic, and this is unique to that single session and recycled instantly when the connection closes. The complete transaction example, loading a web page. The request gets sent and your PC targets port 443. Your OS assigns a random source port, like 52,140 to that tab. The server receives that data on port 443, processes it, and notes the return IP is, the return port is 52,140. The server sends back your IP using source port 443 and destination port 52,140, and your PC receives that traffic on port 52,140 and routes it to the correct browser tab. The socket concept. So defining a network socket involves IP addresses route data to the host. Port numbers routed to the application. The socket is the precise combination of both, written as IP port. This acts as a software abstraction layer managed by the OS kernel, and applications read and write to sockets like an open communication channel. The dynamic duo source versus destination sockets. A complete connection requires a four tuple binding of two distinct sockets. The destination socket, the remote host listening endpoint, such as 203.0.113.50 on port 443, and the source socket, temporary client-side sending endpoint, like 192.168.1.15 on port 52,140. So one port can handle thousands of sockets simultaneously. The OS tracks the connections using the full four tuple, not just the destination port. This allows a single web server port to segregate thousands of concurrent users. User 1 on a laptop to the destination. As we can see here, these are different IP addresses that are all connected with the same information. And then we go down to user 1 from 192.168.1.15 to 52,141 to destination 203.0.113.5 on 443, the unique client port. The unique four-tuple combinations ensures data routes to the correct memory thread without overlap. For different types of web network sockets, we have the stream sockets, TCP. This is connection-oriented, requires handshake, and guarantees data order and delivery. And datagram sockets, UDP. This is connectionless, fires packets instantly, without delivery verification to minimize overhead. Address Resolution Protocol, or ARP. The problem that ARP solves is that the OS builds data with destination IPs, but local switches can't read layer 3 logic. Switches require a layer 2 MAC address to deliver signals to physical network cards. ARP translates known IPv4 addresses into physical hardware addresses on that local network. ARP works with an ARP request or broadcast, where the PC sends a frame targeting the target IP with the destination MAC address, Alt F. The switch floods this broadcast frame out to every port to all connected devices. The ARP reply unicast non-matching devices drop the packet instantly, and the device owning the target IP sends a direct unicast reply with this MAC address back to your PC. For efficiency optimization, we have the ARP catch. Broadcasting for every packet would overwhelm the local network bandwidth, so the OS stores the discovered IP to MAC mappings in a temporary internal ARP catch database. Next, packets skip broadcasting and pull hardware destination IDs straight from memory, and entries expire and auto-delete after 2 to 20 minutes to keep local network map updated. And the security vulnerability with ARPs is ARP spoofing. ARP lacks authentication. Devices implicitly trust any reply, even if it's unsolicited. The attack involves a malicious actor sending fake replies, claiming to be the default gateway router. And the impact here is that the PC poisons this ARP catch, routing outbound traffic to the attacker for interception. Then we have static versus dynamic addressing. Every device needs an IP, subnet, default gateway, and a DNS to communicate. For static, this is manually entered by an administrator, permanently locked in place. For dynamic, this is automatically assigned by a network infrastructure and is temporarily leased. For static addressing, the configuration is typed directly into the device's network settings. The IP remains identical across reboots and power cycles, and it requires tracking to avoid duplicate IP conflicts. Infrastructure that must stay at a fixed location, like routers, switches, servers, and printers, are what primarily uses this. And then we look at dynamic addressing, or DHCP. This automates configuration through the Dynamic Host Configuration Protocol, DHCP. It triggers instantly when a device connects to Wi-Fi or Ethernet, and it does so in 4 steps. The first step is discovery. Unconfigured client broadcasts to find a DHCP server. The offer happens where the server responds with an available IP address option. The client then replies to the claim the specific IP address, and then the server logs the client's MAC and delivers full network parameters. The concept of the DHCP lease is that dynamic IPs are leased for a specific duration, like 24 hours to 8 days. The client silently requests a lease renewal once the timer hits the 50% mark. If a device disconnects permanently, the lease expires and the server reclaims the IP. I'm going to skip the summary there because just went over that. So then we move into the local traffic cop, or switching. Switch learns the neighborhood by beginning with an empty table and building a map of the network layout dynamically. Sorry, excuse me 1 second. Okay, sorry. All right, so then we move into observation. This inspects the incoming source MAC address of any frame crossing an interface and pairs that address with the receiving port in memory. The flood, unknown unicast, routes the frame out of every single active port except the source interface if the destination MAC address is not yet listed in the table. And the update It captures the source MAC address of the target device when it transmits a reply, recording its exact location to complete the map. The lookup, or the KM table in action, it performs rapid hardware level lookup when a new frame arrives. It identifies the exact interface associated with the destination address and establishes a temporary isolated private circuit between the ports. This prevents other devices from seeing traffic to minimize collisions. We can see in the CAM's table structure here, and the term technology behind the speed. We have RAM, which searches memory addresses for data. CAM does the exact opposite. Queries hardware using the MAC address to instantly get the matching port. It executes at wire speed with virtually zero transmission delay, and it's checked on enterprise equipment using commands like show MAC address table. Routing, global navigator. We have the logical map, the routing table. This acts as a database of known network destinations instead of tracking individual hardware addresses. This instructs the device which outbound path or gateway to use to reach the specific remote subnet. Destination network is the target IP neighborhood. The next hop is the next gateway router's IP address along the path. The metric is the calculated cost or distance of a route, and the outgoing interface is the physical port used to exit the router. The best path is chosen through evaluating potential paths to a destination using a strict 3-tier hierarchy. The longest prefix match chooses the most specific routing rule available, and the administrative distance, AD, rates the reliability of the routing source. The metric here chooses the lowest path cost when reliability is tied. Static versus dynamic routing. Static routing routes are hard-coded manually by an admin, while dynamic routing routers automatically share maps and adjust to changes. Operational comparison. The operating layer switch uses layer 2 while router uses layer 3. Switch reads MACs while routers reads IPs. Switches use the CAM table while routers use the routing table. And the switch connects to local devices while routing connects different networks. Broadcast domains versus collision domains. Collision domains are a physical network section where packets can crash if devices transmit simultaneously. The legacy hub problem is hubs repeated data out of all ports, forcing everyone to share one channel. This creates an isolated microsegment between sending and receiving ports. And every individual port on a switch is its own independent collision domain. The noise solution here, the logical network boundary where a broadcast frame reaches and is processed by every host. The limitation is that switches must flood layer 2 broadcasts out of every active interface. The router solution here is that routers act as a boundary that drops layer 2 broadcasts instead of forwarding them. And the result is that it keeps local network chatter isolated inside a single subnet. And to compare them, the core issue is that collision domains involve physical data crashes while broadcast domains involve logical shouting to all endpoints. Collision domains are split by switches and routers. Broadcast domains require routers or VLANs. A collision domain spans a single port/link, while a broadcast domain covers an entire subnet. And scaling entirely on switches creates one huge broadcast domain, causing severe latency. Default gateway, local versus remote. This evaluates the outbound packets using its own IP and subnet mask. The local path directs traffic to the local switch via ARP if the target's on the same subnet, while the remote path routes traffic to the default gateway if the destination is external. Why the IP matters? Because it functions as the explicit next hop for all internal and external traffic. This needs a configured entry in the local IP stack, usually the first usable host IP. This serves as the universal fallback instruction when no explicit route exists. So first it strips the frame and it receives the frame and discards the local layer 2 header, MAC header. It analyzes the layer 3 destination IP against its routing table and hands off the it re-encapsulates the packet into a new layer 2 frame for the outbound link. This retains the ability to talk to local resources like printers or network storage, maintains peer-to-peer communication with workstations on the same local segment, and fails instantly when trying to access global domains or external networks due to no defined exit path. At the end of the day, this acts as boundaries separating the local 2 layer switching from global layer 3 routing. Someone have a question? Or yes, I can. Layer 2 versus layer 3 devices. Layer 2 switch operates entirely within the boundaries of a physical MAC address. This uses specialized ASIC ASIC chips to forward local frames between ports at wire speed. And the limitation here is that it's blind to IP topology. It can't route traffic between different subnets or VLANs without external routers. Layer 3 multi-layer switches combines high port density with an integrated routing engine. It uses high-performance ASICs to handle both layer 2 switching and layer 3 IP routing directly in hardware. The advantage here is that it eliminates bottlenecks by routing local traffic between departments' hardware speeds. The primary strengths is multi-layer switches excel at high-speed internal local routing, while routers excel at intelligent external and WAN routing. Switches offer high-density Ethernet ports, while routers provide specialized connections like fiber, cellular, and serial interfaces. Switches support basic routing protocols, while routers handle advanced security policies, VPN tunnels, NAT, and traffic shaping, and switches sit deep inside the campus, core, or distribution layers, while routers sit at the very edge as security gateways. Static versus dynamic routing. Static routing is the manual map. The network admin manually codes explicit paths into the router configuration. The traffic paths remain fixed unless changed by a human. This conserves CPU and RAM by avoiding complex algorithms or updates, and it lacks no path healing. If a link drops, traffic fails instantly. This becomes an unmanageable burden on large networks. Then we have dynamic routing, the self-updating map. This uses background protocols to let routers discover paths and share maps automatically. This detects failures in real time and calculates detours within seconds. It requires one setup, natively maps out expansions and changes. It consumes memory, CPU, and bandwidth for continuous updates, and demands higher engineering skills to design and troubleshoot. Big players in dynamic routing is OSPF, open shortest path first. Interior protocols used inside a single corporate network or data center. Maps pass mathematically using link bandwidth. And then we have BGP, or Border Gateway Protocol, which is an exterior protocol that glues the global internet together. This routes traffic based on the path attributes and ISP peering agreements. Architectural application. For configuration, we have manual hands-on entry, static versus automatic neighborhood. We already went through that. Skip that. Packet is rewritten. The rule of persistence first change. Layer 3 IP is constant end-to-end logical addresses. It identifies ultimate sender and receiver, while the layer 2 is a temporary hop-to-hop physical address rewritten at every router interface. Step-by-step rewriting process. Hop 1, the laptop to home router. Layer 3, source IP, the laptop switches to the destination, and the destination IP, the web server. Layer 2 is the source MAC, the laptop, to the destination MAC, the router local interface. The action here is that the local switch uses layer 2 address to deliver the frame to the gateway. The second hop, the router strip and rip. The router peels off and discards the invalid layer 2 header. It inspects the router, matches the layer 3 destination IP against its routing table. It builds a new layer 2 frame for the next link. The source IP and the destination IP remain untouched, while the layer 2 source MAC and destination MAC get updated. And then hop 3, the final destination delivery. The process repeats at every single routing device across the internet backbone. Final router uses ART to build the ultimate local hardware container. And the final layer 2 is the source MAC, the target gateway, and the destination MAC, the web server. Significance here is that the MAC addresses are strictly local and invisible past the immediate wire segment. Routers don't need to know the physical MAC address of a remote machine across the globe. Separating the local hardware delivery from global routing lets the internet scale. Then we have LAN versus WAN. The LAN, or local area network, is the switch's domain. This connects endpoints within one physical location, such as a home or an office. This uses layer 2 switching to move data via physical MAC addresses. This shares local resources like storage, printers, and internal servers quickly, and it offers high speeds, low latency, and high security since the organization owns the hardware. The WAN is the router's domain. This connects geographically separated LANs across cities, countries, or the globe. This uses layer 3 routing to move packets across networks via logical IP addresses. It connects remote branches, data centers, and cloud environments. It has a lower throughput, higher recurring provider costs, and requires strict encryption. How they connect? The router as the boundary. This acts as the edge gateway with an active interface in both networks. Internal face, the LAN interface uses a private IP address to process traffic from local switches. The external face, their WAN interface, uses a public ISP IP address to route traffic to the internet. The physical boundary is the LAN stays inside your walls while the WAN scales across the public spaces. LANs rely on network switches while WANs require edge routers, and LAN traffic uses MAC addresses while WAN transit requires IP addresses. The DNS hierarchy. The hierarchical architecture. DNS uses a distributed hierarchical delegation model rather than a single database. We have root servers, the top of the tree, directing traffic to the correct top-level domains. The top-level domains, or TLDs, are the next layer, separating domains by extensions like .com or .org. And authoritative name servers are the final destination holding the definitive records for a specific domain. The journey of the lookup happens in 4 steps. First is the query to a root server, where the resolver asks a root server for example.com. The root server doesn't know the IP, but reads the .com extension, and it returns the referral list of IP addresses for the .com TLD servers. Second step, query to TLD server. The resolver queries the designated .com TLD name server. The TLD name server doesn't have the final IP, but knows who owns the domain namespaces. It returns a referral to the specific authoritative name servers for that domain. It then queries to the authoritative server, where the resolver queries to the authoritative server directly. It holds the master copy of the zone files, and it looks up the requested A record, and then returns the definitive IP addresses. And lastly, the resolver catches the mapping based on its TTL and hands the IP to the browser. This works because of delegated authority, because the responsibility flows smoothly from roots to TLDs to authoritative servers, and because of scalability, because there's no single server that stores every record. Recursive and iterative queries. Recursive queries are get me the answer no matter what. Your laptop sends a single query to the local DNS resolver demanding a definitive answer. The client passes all the workload to the resolver, sitting silently while the resolver handles the upstream search. The resolver must return either the exact target IP address or an explicit error message. Iterative queries are the I don't know, but ask this guy next. This is used by the resolver to communicate with the different tiers of the DNS hierarchy. The query server doesn't search or forward the request. It just hands back their best referral link it has. The server replies with a referral address, forcing the resolver to independently call the next server. And the distinction here, we have the client to local resolver link. This is strictly recursive. The client makes one request and expects the final answer. Local resolver to DNS hierarchy link, a series of iterative relationship. The resolver follows referral from root to DLD to authoritative server. And the benefit here is end user devices don't manage complex lookups. The global root/TLD servers avoid heavy processing loads. 1 second. We're getting there. So then we have the DORA process, DHCP, the initialization process. DHCP uses a 4-step handshake called DORA to assign IP addresses, subnet masks, default gateways, and DNS servers. First step, it relies on a mix of layer 2 and layer 3 broadcast and unicast because the client starts without an identity. First, the DHCP discover broadcast. Purpose here is the unconfigured client shouts across the local network to find any active DHCP server. The switch floods this frame out of all ports, so all local servers receive it. Second step is the DHCP offer. The servers intercepting the discover frame reserves a temporary IP and offers it to the client. The client receives the proposed IP, lease duration, and server identity. Then we have the DHCP request, where the client selects an offer and formally requests to book that specific address. The chosen server prepares the lease, while the unselected server releases their temporary reservation. And then the DHCP ACK. Purpose here is to show the chosen server finalizes the binding, maps the client's MAC to the IP, and sends the configuration. The client builds the IP parameters to its interface and becomes active on the network. Our guardrails here consist of the subnet constraint, where broadcasts can't cross routers. If the server is on another network, you must configure a DHCP replay agent IP header helper address to convert broadcast to the unicast. Then we have lease control, where configurations aren't permanent. Clients must renew their temporary lease at a predefined interval. DHCP leases and scopes. For DHCP scopes, we have this defines the boundaries. This is a continuous range of IP addresses available for dynamic distribution on subnet. This includes starting and ending IPs, subnet masks, default gateway, DNS servers, and lease durations. And IPs manually lock out from the pool to reserve them for static infrastructure like routers and printers. DHCP lease concept. IPs are never granted permanently. They're issued a lease with a countdown timer. This is used in high turnover public spaces like coffee shops to prevent address depletion. This is used in stable corporate networks for desktop workstations for long leases. And then the server maps each leased IP to the client's unique physical MAC address. The renewal and rebinding process, we have T1 timer, 50% mark renewal. The client sends a DHCP request to the original server. An ACK request resets the clock to 100%. And then the T2 timer at 87.5% for rebinding. If the original server is offline, the client broadcasts a DHCP request to any backup server. And then lease expiration. If the clock hit 0% without a response, the client drops its IP and stops network communication until a new DORA process succeeds. Scope exhaustion here is when the pool runs out. This happens when active devices exceed the total assignable IPs in scope. The impact is that the new devices broadcast a DHCP discover, but the server has nothing to offer, causing the handshake to fail. Symptom here, API PA. The host self-signs a non-routable link local IP from the 169.254.0016 block. And the consequence of this is that the device can talk to local neighbors on the same network switch, but can't access the gateway, DNS, or internet. We can mitigate this with shortened release times. We can force departed devices to release their IPs back to the pool faster. We can move from a /24 mesh to a 254 host to a /23 mesh, which is 510 hosts, to double available spaces. And then we can map critical assets to fixed IPs within scope based on their MAC addresses. Or the local translator. Why is ARP crucial? It bridges the gap between layer 3 logical IP addresses to layer 2 physical hardware MAC addresses. Conflict here is that apps use IPs to communicate, but local network cards and switches only read MAC addresses to move frames. We have 4 steps here. The first step is consulting the local catch. Before broadcasting, a device checks the ARP catch or the RAM table for a recent IP to MAC translation. A device finds the MAC, encapsulates the packet, and sends it instantly without network overhead. No entry is found, so if the catch misses it, no entry is found, so the device buffers the packet and starts a resolution handshake. Step 2 is the broadcast request. The sender transmits an ARP request broadcast frame across the local network. Source IP and MAC are the sender's destination. Destination IP is the target, and destination MAC is alt S. The switch floods this broadcast out of all active ports so every host inspects it. Then we have step 3, the unicast reply. The comparison where the host with non-matching IPs drop the frame. The match where the target devices process the packet, catches the sender's info, and builds a targeted ARP reply. The source IP and MAC are the targets. The destination IP and MAC are the original senders. And this is sent as a direct unicast frame. The switch routes it straight to the sender's port. And then we have step 4, the final encapsulation and catch store. The sender receives this reply, saves the new mapping to its ARP catch, and pulls the buffered packet from memory. It wraps the packet in an Ethernet frame stamped with a new destination MAC address and releases it. The switch reads the MAC and delivers the frame cleanly to the target port. And we have a couple guardrails here, including the layer 3 boundary. ARP can't cross a router to reach its external subnet. A host ARP for its default gateway IP instead of the final remote IP. And then catch expiration, where entries are ephemeral and erase themselves after a few minutes to clear outdated mappings from hardware changes or DHCP updates. The ARP catch. The catch is a performance engine. The ARP table is a high-speed volatile RAM lookup table built into an OS network stack. The problem here is that the network broadcasts force every local device to interrupt its CPU to evaluate the frame. Broadcasting an ARP request for every single data packet would quickly choke network bandwidth. The solution here is storing successful IP to MAC mappings locally, which lets the host bypass network discovery for subsequent packets, encapsulating and shipping data across the network in microseconds. Anatomy of an ARP table entry. A standard ARP catch contains 3 primary attributes for each entry. The internet address, the logical IPv4 address of the remote endpoint, their corresponding 48-bit hardware MAC address used unique for that device, and the type. This denotes how it was learned, whether it was dynamic or static. Why they must expire. Dynamic entries are governed by a catch aging timer that typically erases them after 2 to 20 minutes, which is critical for handling IP reassignment, network interface swaps, in mitigating scale entry bloat. The cybersecurity angle here, disrupting subversion, shortcuts lifespans serve as a basic architectural guardrail against local network threats. We can limit ARP poisoning and spoofing. It limits ARP poisoning and spoofing when attackers send fraudulent ARP requests to poison a target's cache, mapping a gateway's IP to their MAC to intercept traffic. And self-healing buffer, the expiring caches force the host to issue fresh, legitimate ARP requests periodically, giving the network recurring opportunity to clear out unauthorized mappings. Then we have gratuitous ARP, or GARP. The unsolicited nature of GARP. Traditional ARP is reactive, while gratuitous ARP is a proactive and completely unsolicited. It issues a definitive broadcast to the subnet, saying, I hold this IP and this is my MAC address. The unique packet architecture, both the source IP and destination IP match the sender's own IP address. The source MAC address is the sender's physical address, and the destination MAC address is the universal layer 2 broadcast. This identical source and destination IPs signal to other devices that this is a gratuitous update. The 3 steps of this starts with duplicating the IP address in conflict detection. A booting host broadcasts a GARP. Normally, no one should reply. If another device already uses that IP, it replies. The newcomer logs the conflict error and disables its interface to prevent destabilizing the network. Then we update and remove remote neighbor ARP catches. When a device's IP to MAC mapping changes, local neighbors would hold stale entries until timers expire. A GARP broadcast forces all nodes to update their local ARP catches instantly without dropping active sessions. And then lastly, we have high availability failovers and virtual IP migrations. In clustered environments, backup routers share a floating virtual IP, VIP. If the primary unit fails, the standby assumes the VIP and floods a GARP. Surrounding switches intercept it and instantly update their CAN tables, rerouting all traffic to the new physical link in milliseconds. Last little leg here. A few more slides. The interdependence, a packet's first second. Phase 1, boot up and identity acquisition DHCP. Problem is a workstation boots with a blank network stack, no IP, no subnet boundaries, and no internet access. The execution here is that the device runs a 4-step DORA broadcast / unicast handshake, which stands for discover, offer, request, and acknowledge. The result is that the host gains its network identity parameters, such as its host local IP, subnet mask, default gateway, and DNS server. Phase 2 is the name resolution, or DNS. The problem here is that the user inputs google.com. Hardware can't parse alphabetical text strings. It requires binary logical IP addresses. The execution is that the host creates a DNS query destined for its resolver. We have the logic step where the host notes 8.8.8.8 is external and routes the packet to the default gateway, and the return is the DNS tree resolves the request and returns a live IP. The result here is that the host holds the final logical roadmap destination, in this case 142.250.1.1. Phase 3 is the hardware delivery localization, ARP. Problem is that the app is ready to transmit data to our new roadmap destination. The host sees the destination is remote, meaning it can't talk to the server directly, so it must drop the packet at the gateway, but it lacks the gateway's physical destination MAC address. The host turns to ARP to bridge the host turns to ARP to bridge the physical gap. First, it starts with an inquiry where it finds no entry in its cache. The host broadcasts an ARP request asking who owns this IP address and to send your MAC. The gateway router intercepts the broadcast and replies with a unicast frame saying what the interface is. The result is that the host stores the hardware mapping in its volatile cache. And finally, with all protocols executed, the host builds and releases the outbound frame, including the layer 3 source IP and destination IP, and the layer 2 source MAC and destination MAC. The core protocol highlight here is that the IP header determines the ultimate macro destination globally across the entire journey, while the MAC frame determines exactly which physical piece of local hardware takes custody for the next micro hop. IPv4 exhaustion problem. We had the scaling crisis where IPv4 addresses ran out because architects didn't anticipate billions of globally connected devices. Designed in 1981, IPv4 uses a 32-bit addressing screen. What's happening? What are you doing? Sorry about that. IPv4 uses a 32-bit addressing scheme with a hard mathematical limit of 4,294,967,296 unique addresses. The inefficiency of classical routing, early internet addresses were distributed using rigid, highly inefficient blocks. We had 3 classes. Class A was given to mega corporations. Class B was given to mid-sized entities, and Class C was given to small businesses. By the early 1990s, the web's explosion growth proved IPv4 out within years. And why NAT was a patch for this, but a Band-Aid fix. The standardized in 1994, NAT was the short-term Band-Aid to delay the exhaustion, not a permanent architecture. It works by dividing the IP universe into private internal networks and public internet. The mechanisms of this patch include private spaces. RFC 1918 set aside 3 IP blocks reserved strictly for internal use. We have the 10.0.0.0/8 for massive enterprises, 172.16.0.0/12 for medium networks, and 192.168.0.0/16 for small home or office networks. This has infinite reusability since every network globally can reuse these exact private IP addresses simultaneously because public routers drop them. Address algorithm aggregation, an ISP assigns one public IP to an entire household gateway router. The router uses NAT to multiplex all internal traffic across that single public presence. And the success in architectural side effects. NAT prolonged IPv4's lifespan for decades, but broke a foundational internet design principle, end-to-end transparency. NAT blocks unsolicited inbound connections, forcing complex workarounds for real-time video calls, VoIP, and gaming. Boundary routers must open every packet header, rewrite the IP and port, recalculate checksums, and track state mappings in memory, adding latency. And because NAT effectively fixed the immediate crisis, the industry delayed a massive migration to IPv6. IPv6 uses 128-bit addresses, yielding 340 undecillion IPs, removing the need for translation patches entirely. Inside versus outside. Inside versus outside addresses. The framework of prospective NAT terms are defined by 2 factors from the perspective of the edge router, location inside or outside, in perspective local/global. Inside versus outside, physical location of the device. Inside is your private network and outside is your public. And for local and global, how the IP looks at the header. Local is only visible inside your LAN, and global is only visible across is visible across the public internet. Sorry. 4 key NAT terms. We have inside local. This is the actual private IP assigned directly to a host on your LAN. The inside global, which is the public IP representing your inside device to the outside internet. Outside global, the real globally routable public IP assigned to a server on the internet. And outside local, the IP of an outside host as it appears to nodes inside your LAN, typically identical to outside global. Step-by-step packet header transformation. Scenario here is host 192.168.15 sends a request to Google server via an edge router at a public IP 203.0.113.1. First, the outbound transit inside LAN, source IP 192.168.1.5, inside local to destination IP 8.8.8 outside local. We have the second step, which is public flight across LAN, source IP 203.0.113.1 inside global to destination IP 8.8.8.8 outside global. Inbound response from internet source IP 8.8.8.8 outside global, destination IP 203.0.113.1 inside global, and then local delivery handoff back to LAN. Source IP 8.8.8.8 outside local, destination IP 192.168.1.5 inside local. The architectural purpose of outside local and global differ only during complex scenarios like overlapping networks. If two merging companies use the same private subnet, standard routing fails due to IP duplication. The router solves this by translating the partnered network's conflicting IPs to a unique simulated private block. This alternate block acts as an outside local address space so the host can communicate without readdressing it. Static net, one-to-one. The one-to-one concept that static net creates a fixed permanent mapping between a single private IP and a single public IP. This relationship is hard-coded in the router's memory and never changes or times out. This is necessary because standard PAT blocks unsolicited inbound connections, which breaks hosting capabilities. Web, mail, and VPN servers require a predictable public address so internet users can find them. Traffic can safely start from either direction, outbound or inbound, and pure static net passes all 65,535 ports to the internal host without restrictions. Think of, we'll skip the scenario here. We have some instructions on how to configure a static net if anyone's interested, but we'll move on here to verifying the static net translation table. The mapping stays in the net table even if the server is off and no traffic is moving. Command router number, router hashtag show IP net translations, and the output shows 203.0.113.50 permanently aligned to 192.168.110. Outside fields show as -- until a live session starts. Static net doesn't conserve IPs. It's a strict 1-to-1 ratio, meaning hosting 5 servers requires purchasing 5 public IPs. It misses out on the address saving benefits of making it expensive for large deployments. Dynamic net. The pool allocation concept. Dynamic net maps private IPs to public IPs using pre-configured finite groups of public routing entries. Public addresses are treated as a shared resource handed out from a pool of first-come, first-served basis. An internal host, like 192.168.1.11, initiates an outbound connection. The router intercepts the packet and grabs the first vacant public IP from the pool. The router binds the 2 addresses in its active translation table and rewrites the packet header. When the device goes idle, an inactivity timer counts down to 0, tearing down the mapping and returning the IP to the pool. Pure dynamic NAT is a strict one-to-one translation mechanism per active session, and it can't overlay multiple devices onto one IP. The limit here is that if your pool has 10 public IPs, only 10 internal hosts can actively communicate with the internet at once. An 11th device trying to go online while the pool is full gets dropped, causing connection timeouts until an IP is free. We can verify this. The translation table stays completely blank until initialization. If no traffic is moving, we can use router show IP NAT translations, and this displays live ephemeral bindings tracking inside local hosts to their precise external destination. Port address translation. A many one-to-one architecture PAT or NAT overload allows thousands of internal hosts to simultaneously share a single public IP address. It achieves this many-to-one setup by tracking and modifying layer 4 transport port numbers, TCP and UDP, along layer 3 IP headers. Multiple LAN devices often choose the same local source port, such as two phones using port 4500, which would cause a collision and return traffic arrives. To fix this, the router rewrites the private inside local IP address to a single public inside global IP and assigns a brand new unique ephemeral port from 1024 to 65,535. The router logs this mapping in its translation table, keep each internet connection distinct. We have steps here on how to configure it. You use this when the ISP assigns just one public IP to your router's WAN. You would match the LAN, bind the WAN interface with overload. You would use overloading to scale out by overloading across small blocks of assigned public IPs. You define the pool in ACL and bind it with overload. And then last, you would have your internal and external. We can verify the PAT operations in the state table. Running the verification command yields the protocol specific mapping, tracking exact port numbers to separated by colons with router show IP NAT translations. Two devices using the same IP and two devices use 192.168.110.4500 and 192.168.111.4500. The router translates them to 203.0.113.1 and 203.0.113.1 to safely separate return traffic. PAT is the ultimate scaling tool for IPv4 consideration, letting thousands of active devices share a single public IP by utilizing over 60,000 unique ports. Almost there. The NAT translation table. A NAT translation table is a high-speed, stateful database in RAM that tracks all boundary network traffic. With PAT, hundreds of LAN devices simultaneously send packets to the internet using a single public IP. And the solution is that the table ensures returning packets match the exact internal device screen that requests them instead of being dropped at the parameter. The anatomy of this: for every outbound connection, the router logs a row tracking these values. We have the protocol, inside local, inside global, and outside local/outside global. The state mechanism in tracking live connection: we have this scenario where a laptop and smart TV open connections using identical ports, 4433. A session 1, the laptop uses TCP inside global 1 and 2, 168.115 on 4433. Inside global, we see the 203.0.113.1 50,001 outside global, all that. The session 2 protocol TCP inside local 1 and 2, 168.122.4433, and inside global is 203.0.113.1 on 50,002, and outside global 151.101.1.140 on 4443. This return traffic arrives from Netflix, destined for the public port. The router searches its table for the matching inside global port assignment. It hits a match on the smart TV row, rewrites the destination headers, and drops the frame into the LAN switch. Routers use inactivity timers to purge dead-end trees and prevent RAM exhaustion. It's held open for up to 24 hours unless a clean teardown signal, fin/reset, scrubs it within minutes. Lacks a close connection signal, erased aggressively after 30 to 180 seconds for complete silence, and is cleared almost instantly, typically within 10 seconds after the reply frame is translated. Manual commands for table inspection on Cisco iOS. We see here routers show IPNet translations, routers show IPNet statistics, and router clear IPNet translation. NAT and PAT and security. So NAT and PAT were engineered to delay the IPv4 exhaustion, but their architecture creates a powerful first line of defense. By splitting networks into private and public zones, NAT acts as a one-way mirror where internal devices look out, but external devices can't look in. So first we have masking the internal network topology. NAT works attacker reconnaissance through topology hiding because visibility equals vulnerability. To an external scanner, your entire network appears as a single device, the router's public IP. Attackers can't see how many devices live behind the gateway, their OS types, or subnet structures. Because RFC 1918 IPs are non-routable, internet attackers can't send packets directly to an internal machine. And then we have state-driven unidirectional filtering. The NAT table inherently enforces the behavior of an implicit stateful firewall based on who starts the handshake. When a LAN host connects to an external server, the router logs session and permits the requested return traffic to pass. If an internet scanner probes your public IP, the router drops the packet immediately because no matching state entry exists in its table. And then we have the critical security blind spots of NAT. NAT is a translation mechanism, not a security tool, and this leaves major defensive blind spots. NAT only rewrites headers at layer 3 and 4, and it can't scan payloads from malware, allowing infected downloads to pass freely. Static NAT report forwarding pokes a permanent hole through the shield, exposing an internal services to direct attacks. If malware infects a host internally, its outbound command and control connection looks like a legitimate web browsing to the router, so it gets translated and allowed. Security takeaway here is that NAT eliminates uninitiated inbound network attacks, but modern threats target allowed outbound paths via phishing and web exploits. You must supplement NAT with true firewalls, endpoint security, and network segmentation. How did this one end up here? This one should have been earlier, but we have private IP ranges. The foundational allocation standard, RFC 1918, permanently set aside 3 distinct blocks of the IPv4 space strictly for private internal networks. These blocks let home and businesses build internal network structures free of charge without registering or with regional internet registries. Do we have, sorry, that's a repeat from an earlier slide. So yeah, now we have the conclusion, the automated perimeter. DHCP continuously manages the transient internal identities to maximize addresses efficiency. ARF dynamically links physical hardware to logical roadmaps to handle local delivery. NAT and PAT patches the core scaling limitations of IPv4 by pulling public resources. For scalability, we can combine RFC 1918 private ranges with PAT to let networks scale indefinitely under single public footprints. Localized caching, like ARC tables, NAT state engines, minimize CPU overhead and prevents network choke points. And the perimeter acts as a one-way mirror, providing an implicit firewall filtering and topology hiding against inbound threats. While PAT and DHCP extended IPv4's lifespan for decades, they remain complex engineering workarounds. Migrating to a native 128-bit IPv6 architecture eliminates the need for translation patches completely, restoring true end-to-end transparency. Whew. That was, I apologize for how much longer that was than I intended, but that wraps it up. Does anybody have any questions before we do a quick quiz? There's a link in the chat for you guys. You will see on my screen when you look and join, there will be the questions and the answers written out. And on your screen, you'll see shapes and colors that you can choose from. And that's where you'll select your answers based on what's on my screen. And anybody who wants it, once we finish here, you can feel free to reach out to me and I'll gladly send you the link so you can take this on your own time as well. All right, because I used so much time already getting us started, getting us going through that, I'm going to get us started on this now. The link is there. Anybody who hasn't joined yet can join anytime during the quiz here. And then, like I said, you can see. We got 5 people. All right, I think good to go. All right, so just to reiterate, you're going to see the answers and questions on my screen. You're going to answer on your own screen. I'll read them out loud for you guys as well as we go. Awesome, we got everyone. Let's get started. Thank you again for your patience, everyone. What is the primary purpose of a device broadcasting a gratuitous ARP message upon joining a network? To request a new IP address from a server, to detect if another device is using its assigned IP, to resolve a website domain name to an IP address, or to encrypt the data frames leaving its local interface. $15 seconds left. All right, so here we are looking to detect if another device is using its assigned IP address. GARP checks for duplicate IPs on the local segment to prevent conflicts. To request a new IP address from a server, requesting an IP address from a server is handled by DHCP, not ARP. Great job, guys. What type of frame does a host send first during the DHCP DORA process to locate an available address server? Unicast web request, a local broadcast discover frame, an iterative DNS query packet, or a static NAT translation request? Seconds left. Excellent, guys. Don't need to explain that one. When your computer needs to send a packet to an outside website like google.com, where does it physically send the frame? To the MAC address of its default gateway router, directly to the global root zone servers, to the universal layer 2 broadcast address, or to the authoritative name server inside the LAN? Thirty seconds left. Ten seconds for me. So we are sending it to the MAC address of the default gateway because local hosts forward all off subnet traffic to their default gateway to be routed directly to the global root zone servers. A local host can't jump directly to a root server without exiting its LAN. Let's go, guys. Why can millions of different homes and businesses all use the private IP address 192.168.1.1 simultaneously? Private IPs are automatically encrypted by standard browsers. They're managed directly by global Anycast root registries. They belong to the IPv6 space, which allows endless copies, or public internet routers drop them, keeping them localized. All right, so we are looking at the public internet routers dropping them and keeping them localized because they are non-routable to the internet. They can't be they can be reused internally everywhere. Private IPs are automatically encrypted and stored by browsers. Browser encryption, like HTTPS, does not alter or hide network routing IPs, and root registries manage public DNS mapping pointers, not local private IP spacing. Good job, guys. And it's got a nice streak going. Which NAT term describes the actual private IP address assigned to the workstation inside your local office LAN? Inside local, inside global, outside local. Thirty seconds. Fifteen seconds. So we're looking at inside local. This inside local represents the real private RFC 1918 address assigned to an internal host interface. Inside global is the public IP address that represents the internal host to the outside world, while outside local is how an external host address appears to the internal network. So, guys, why does the standard port address translation PAT router modify layer 4 source port numbers on outgoing traffic? To scramble the payload to prevent eavesdropping, to force the local host to request a brand new DHCP lease, to allow multiple local devices to share one public IP, or to bypass the need for a default gateway infrastructure. Twenty seconds left. Right. So to allow multiple local devices to share one public IP, this uniquely tracks ports. Uh, Unique tracking ports ensure returning traffic maps back to the correct host. Um, Modifying the port numbers is done for tracking traffic routing, not data encryption. And then PAT runs directly on the default gateway router to transport passing traffic. Ooh, head fees moving up. What happens to an unsolicited inbound connection attempt from the internet if it hits the standard PAT router? The router forwards it to every device on the internal LAN. The router checks if its table, finds no match, and drops it. The router converts the packet into a recursive DNS query, or the router automatically assigns it a static inside local IP. So, router checks the table and finds no match and drops it. If no internal host requests the connection, the router discards the packet. The forwarding unsolicited traffic to all devices will create a massive security flaw, and routers can't convert transport layer data packets into application DNS queries. Why does a router keep a stateful NAT translation table inside its volatile memory? To permanently archive every website a user visits for auditing, to map returning internet data back to the correct local host, to translate human readable domain names into logical numbers, or to block all outbound connections from leaving the enterprise. Excellent. Great job, guys. Why must a router use relatively short inactivity timers to automatically purge UDP entries from its NAT table? UDP is connectionless and sends no official closed signal. UDP travel is non-routable on the public internet backbone. UDP packets lack a source IP address in their packet headers. UDP requires a permanent static mapping to pass through a firewall. Excellent. That we use because there's no teardown flag. The router must use the timer to prevent RAM bloat. What was our other one? UDP is a standard, highly common internet transfer protocol. What is the main operational disadvantage of using static NAT for internal services instead of using PAT? It blocks external internet users from accessing web assets, is highly inefficient, and uses up one public IP per server. It dynamically changes the server's public IP every hour, or it forces the server to use an IPv6 address profile inside. Static NAT requires a strict 1-to-1 ratio, saving no public address space. Static NAT is intentionally selected to allow external users to connect inbound, and it maps standard IPv4 addresses and does not mandate an IPv6 migration. That's a good word, guys. What is the fundamental difference between a recursive query and an iterative query in DNS? Recursive queries require a final answer. Iterative can refer. Recursive queries use TCP. Iterative queries use local ARP. Recursive uses MAC tables. Iterative updates routing. Recursive queries are private. Iterative queries are public. Root servers only point to TLD servers and do not hold any individual domain zone files. The authoritative server holds the actual read-write database records for a domain. Which server in DNS hierarchy holds the definitive official zone files and resource records for a specific domain? I read the wrong one for that last one. Sorry about that. An Anycast root server, an authoritative name server, a top-level domain, or a client sub resolve server. The authoritative name server holds the actual read-write database records for a domain. the root servers only point to TLD servers and don't hold the. Oh, that was the one that I read the last one. Sorry. For the last one, real quick before I forget, just to give you the reason for the correct answer on the fundamental difference between recursive and iterative. Recursive demands the final IP or an error, while iterative follows referrals. Sorry about that. Great job, guys. What problem does the introduction of the Anycast routing solve for the Internet's 13 logical DNS root server addresses? It allows routers to bypass the NAT topology shield completely. It translates the private RFC 1918 networks into Class A addresses, distributes traffic globally across the thousands of networks servers. It forces all global websites domains to use a single A record. Ten seconds left. Excellent, guys. What does a standard DNS A record provide to a recursive resolver during a lookup sequence? An alternate domain name alias for a specific web target, the IPv4 address that maps to a human readable host name, the physical hardware MAC address of the destination server, and a new dynamic port allocation out of the PAT gateway protocol pool. So an A record provides a 32-bit IPv4 logical address for a specific domain. Mapping a host name to another host name alias is the job of a CNAME record. Guys, almost there. Why was network address translation originally invented in the early 1990s? To act as a short-term patch for IPv4 address exhaustion, to encrypt internet traffic from hackers, to replace the human readable DNS lookup system entirely, or to eliminate the need for layer 2 MAC addresses on the switch. It was created to slow down the consumption of the limited 32-bit address space. NAT coexists with DNS and does not resolve human readable domain text. What security benefit does topology hiding naturally provide to an internal business network? It encrypts the payload of all internal database transfers. It stops the internal use from visiting unapproved external sites. It automatically cleans malware attachments from email servers, or it makes internal host IP addresses invisible from internet scan. Attackers only see the single public IP of a router, shielding the LAN layout. Topology hiding only masks the network addressing structure. It can't encrypt data. More left. Why is NAT considered an insufficient standalone defense against modern client-side attacks like phishing? It blocks the user from initiating outbound web requests. It does not inspect packet down payloads for malicious content. It forces all local office workstations to share a single MAC. It leaks private RFC 1918 addresses to public BGP routers.
Mom said I'd get this.
Please don't. Excellent, guys. Sorry, take a second to. What happens when an internal host successfully receives a clean DNS reply containing a target website's public IP? Automatically overwrites its own inside local address. It transmits a dynamic PAT overload frame to the root zone. It checks the subnet mask to see if the target is local or remote. It clears dynamic static mappings inside the local realm. So this step determines whether it can talk to a host directly or must use a gateway. The PAT overload triggers when data passes through the router, not upon a DNS reply. And receiving a DNS reply does not alter a device's local IP identity parameters. Keep it up, guys. 2 more left. You're almost there. Which component of a computer's OS is responsible for initiating a recursive DNS query to a local resolver? To local resolvers. Lightweight stub resolver software, stateful PAT state machine, the border gateway protocol engine, or the physical hardware MAC controller. Twenty seconds left. So the stub resolver is the local component that queries the designated DNS resolver. The MAC controller operates at layer 2 to process raw electrical or optical frames. Right. Last but not least, we got close numbers here. What critical event triggers a router to remove a dynamic PAT translation entry from its active memory ledger? The local host updates its physical hardware interface card. An activity timer expires after a period of session silence. A global root server changes its Anycast allocation profile. the destination web server modifies its canonical CNAME alias. Thirty seconds left. Ten seconds left. Right, so timers ensure old or abandoned entries are purged to save finite RAM resources. Swapping a network card doesn't automatically wipe a router's active NAT tables, and DNS alias modifications are handled by registries and do not alter NAT timers. And with that, we can take a look at the podium before we finish up. Thank you everyone for coming. Thank you for all of your patience. I really did not intend for that to be such a long session. I was honestly shooting for closer to an hour, so I'll make sure next time is much shorter. Thank you again for your patience, everyone.